In this lecture, I will solve two problems. In first problem, we need to determine V0 and ID. V0 is the voltage across this resistance and ID is the current flowing through this diode. If you see these two branches, you will find they are same. In this branch, we have one silicon diode and one 2 kilo ohm resistance. In this branch also, we have one silicon diode and one 2 kilo ohm resistance. So current in this branch is also equal to ID, and current through this resistance is equal to twice of ID. You can easily find out current flowing through this resistance by using the KCL, Kirchhoff's current law, and it is equal to twice of ID. Now we will determine the state of two diodes. 10 volt is the potential at this point and we have to calculate V0. So the direction of current is from left to right, and the direction of current is similar to the direction of arrow in the diode symbol. So the two diodes are forward biased and remain in on state, and I will replace them with their equivalent circuit. So I will quickly draw this circuit in which diodes are replaced by their equivalent model. We are using silicon diodes, so the potential difference is equal to 0.7 volts. I will do the same thing for the second diode. Second diode is also silicon diode, 0.7 volts. 2 kilo ohm is the resistance in this branch. 2 kilo ohm is the resistance in the second branch. We need to calculate V0. V0 is the voltage across this resistance, having the value 2 kilo ohms. ID is the current flowing in the two branches, and current flowing through this resistance is equal to twice of ID. Potential at this point is plus 10 volts. Now I will calculate ID. We will start from this point. And move towards zero potential like this. This is ground, so it is equal to zero potential. We will start from 10 volts and move towards zero potential. So we have plus 10 volts minus 0.7 volts minus 0.7 volts minus 2ID minus 4ID equal to 0. From this equation I can easily calculate ID. 6ID is equal to 9.3 volts. This implies ID is equal to 1.55 milliamps. This is the answer. Now we will find out V0, the voltage across this resistance, and I will start from V0. And move towards 0 volt. So we have V0 minus 4ID equal to 0. So V0 is simply 4 times ID. ID is equal to 1.55 milliamps, and 4 kilo ohm resistance is there. So the unit is going to be volts, and the value is equal to 6.2. So we have 6.2 volts as the answer. Now I will solve the second problem. In this problem, we have 3 PN junction diodes. Plus 16 volt is the potential at this point, and plus 12 volt is the potential at this point. 16 volt is greater than 12 volt, so current will move in this direction, and all the 3 diodes will remain on because the direction of current is similar to the direction of arrow in the diode symbol. This current is I, so current through this resistance is also equal to I, because if we have this situation, like this, current is equal to 2 amps, then current here is also equal to 2 amps, because I1 plus I2 is equal to 2 amps. I will calculate I first, then we will calculate V0. I will start from 16 volts and move towards 12 volts like this, and we will consider the equivalent model of all the 3 diodes. They are silicon diodes, so the barrier potential is equal to 0.7 volts. 16 volts minus 0.7 volts for this diode. I will move in this way, so again we have minus 0.7 volts. Then we have 4.7 I equal to 12 volts. When you solve this, you will have I equal to 0.55 milliamps. Now I will calculate V naught and we will move in this direction towards 12 volts. V naught minus 4.7 I equal to 12 volts. So V naught is simply equal to 12 plus 4.7 multiplied by 0.55, and this is equal to 14.6 volts. So this is the answer that we had to calculate in this problem. In this way you can deal with parallel and series parallel configuration of diodes. I hope all the points explained in this lecture is clear to you. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.